To begin our study of chemical reactions, we're going to spend a little bit of time simply outlining what they are and how we can write them down. In this video, our learning goals will be to talk about the essential change that makes up a chemical reaction, how we represent those reactions symbolically, and some important information that we usually want to include when we talk about a chemical reaction. So what is a chemical reaction? Let's start by looking at some common reactions that we may be familiar with. For example, combustion. It involves some visible changes. It gives off heat. A lot of combustion reactions generate light. Certainly if you light a fire, you're doing all of those things. Acid and metal. You may be less familiar with this, but if you react an acid with a metal, that reaction generates a gas. It's very clear to see. A precipitation reaction is when we might mix two liquids together and a solid comes out. That's certainly a very visible change that one can see in those reactions. Oxidation sometimes involves changing colors, but it always involves oxygen reacting with substances and usually changing their chemical properties, making them more brittle or maybe even stronger. But in any case, it's a reaction that leads to some visible changes. But what do these processes have in common? They all seem very different, and we may not be inclined to think of them as really the same thing. But in fact, what they all have in common is they involve changes in the valence electrons. And in fact, our general definition for chemical reactions in this course is going to be a change in the valence electrons that leads to a new stable state. So how would we represent these reactions? We want to have a nice notation, a nice way of talking about reactions without having to describe them in great detail verbally every time we want to talk about one. Well, we do this using chemical equations, and the simplest way to write down a chemical equation is basically to say reactants go to products. The arrow in the middle there is indicating the direction of the reaction. Now, we'll find out later on in this course that we can actually point the arrow in both directions for many reactions, but for now let's just settle on having our reactants on the left-hand side and our products on the right-hand side. Sometimes there's more than one species among our reactants and products, in which case we would simply add them up. So you can see in this way a chemical equation is very much like a mathematical equation. We're going to add things together on the left-hand side, and they're going to go through some sort of chemical change process, and they will end up as products on the right-hand side. A good example of this might be the reaction of copper with nitric acid. This is a popular demonstration in a lot of general chemistry courses where you might take a penny, which has copper in it, and drip some nitric acid on it. It's a very vigorous reaction, and it has a color change, and it generates a gas. It has basically all the things you want in a reaction that has visible changes. Now, we often want to employ some descriptive labels to talk about elements that are in a chemical reaction. What I've just shown you for copper and nitric acid is what we would call a skeleton equation, and it's just a bare bones description. It lists the reactants, it lists the products, but it really doesn't tell us much of anything else. What other relevant information might we want? Well, for example, we may want to know something about the physical state of the species. We may want to know if they're solid, liquid, or gas. We may want to know if their pure components are part of a mixture. So for example, we often use this label to indicate that something is dissolved in a water solution. The AQ stands for aqueous. We may also want to know the locations of ions. In many cases, they're in an aqueous solution. So now if I take that same equation and fill in some of that missing information, we can see that this really involves a solid piece of copper reacting with nitric acid that's in an aqueous solution. Liquid water is also part of that. It generates a copper ion that's in aqueous solution. It generates a hydronium ion, the H3O+, that's in aqueous solution. And it generates a gas, NO2. Now, we also would like to indicate some of the environmental factors that are around that, because sometimes these are important to determine whether or not a reaction actually happens. These environmental conditions might include things like the temperature, which we always list in Kelvin in this course, although sometimes we stray and we use centigrade, but Kelvin and centigrade are both reasonable to use in a scientific context. We might talk about the addition of heat. We usually indicate this by using the Greek delta sign to indicate heat. We might add electric current. This is a popular way to decompose water. We might use a solvent other than water. For example, we could use methanol, in which case we would just list methanol underneath the arrow in the reactant. So this information that I've indicated here is usually indicated above or below the arrow in a chemical equation. Now, these chemical equations are all change processes. There are other change processes that could be written very similarly. For example, we might represent a phase change. Here's liquid water going to steam. We could write it as though it were a chemical reaction, and it's not a chemical reaction because we really haven't changed the chemical identity of the water, but it's still a change process that lends itself to this sort of notation. We could also use it to talk about dissolving things. So if we want to dissolve salt in water, we might indicate that by saying sodium chloride solid is going to go to sodium chloride in aqueous solution. That's a dissolving process. It also is used often to describe radioactive decay. So, for example, we might talk about the decay of uranium into thorium and helium, which is a particular kind of radioactive decay. So there's lots of different ways we can use this notation. Chemical reactions is the way we're going to be employing it mostly in this course, but I hope this has helped you understand a little bit about how we talk and represent chemical reactions.